So in today's video, we're going to be looking at chapter 5.6, which is discrete dynamical systems. What I'm actually going to do is to split this chapter into two. It's a very long and complicated chapter. So I'm actually going to take out chapter 5.7, and if you would like to read it, by all means go ahead. If you do take differential equations with us at Taylor, you will actually look at chapter 5.7 in differential equations. It's actually a big part of that course. So I don't want to go through it just for the sake of time, because I would have to teach you some differential equations to get to that chapter. But if you would like to read it, or if you have any questions about it, please go ahead and do 5.7. But what I'm going to do is to teach you the basics of it here in 5.6. And it's looking at how we can use systems where you've got something is equal to A times X, okay? So you've got some vector is equal to a matrix times a vector. And we're going to look at these systems where they are iterative, okay? So you're going to continually multiply by A and see what happens at the next step. It's exactly like what we did when we did the spotted owl problem on MATLAB. We would have actually had the other MATLAB assignment would have gone with this chapter, but of course we won't get to that. But what we will be doing here is looking more at that system and looking at how the eigenvalues and eigenvectors of that matrix affect what happens in the system, okay? So we're going to tie what we did with those types of systems where we had like that iterative system where we continually multiply by A multiple times, and we're going to see how the eigenvalues and eigenvectors of A are going to affect that iterative system and look at its look at the long-term behavior, okay? So all of this is going to deal with real-world problems. So I will be taking real-world problems both in this first part and in the second part that I will do for tomorrow's video. And we're going to look at the long-term behavior using something called a difference equation. And that is exactly what we have looked at before. This is the normal form of a difference equation. Okay. So you start out at some initial vector x0. Okay. And what you're going to do with x0 is multiply it by A, and that will give you x1. So x1 is just A multiplied by that initial vector x0. It's the initial state of the thing that you are looking at. When we did it, it was the initial populations of certain ages of owls. So we looked at how many there were in the juvenile. I think it was then the next stage up was like the young adults and then the adult owls. So we looked at the three different age groups and we looked at the initial populations of them. And then you multiply by A and it will tell you what happens after 1 month, what the populations will look like. You multiply by A again, it will tell you what happens at the second month. Okay. So what we are going to do, we're going to assume for what we're going to do that A is diagonalizable. Okay, so A is going to be diagonalizable. When A is not diagonalizable, it does get more complicated, so we're not going to look at that in this course, but we're going to consider A to be diagonalizable. That means if A is an n by n matrix, okay, it means that it's going to have n linearly independent eigenvectors, and it's going to have n eigenvalues. They may not be distinct, but you're going to have the n eigenvectors associated with the n eigenvalues. So the multiplicities of the eigenvalues will match the dimension of each of the eigenspaces. So if A is diagonalizable, that means that we have n linearly independent eigenvectors of A, which we're going to call them V1 through Vn. Okay. And they've got eigenvalues. We're going to call them lambda 1 through lambda n, but we're going to order them in such a way such that they're going to decrease in value. Okay, so I'm going to, when I get my eigenvalues, remember when you say that A is equal to PD P inverse, okay, when it's diagonalizable, and P is formed of the eigenvectors and D has the eigenvalues on that diagonal, you can arrange the eigenvalues on, that diagonal of D in any way that you want, okay? But remember, when you do that, whatever order you put those eigenvalues in, the eigenvectors in P have to be put in the same order. So for each of the eigenvalues, let's say if you've got an eigenvalue that's in the second row, second column on that diagonal entry, that second diagonal entry, the eigenvector associated with that eigenvalue goes in the second column of P. Okay? But if you move it, so instead it's in the fourth entry on that diagonal, then you have to move that eigenvector to be in that fourth column of P. Okay? So you can put them in any order you want, you just have to make sure that the eigenvectors are in the same positions in P as the eigenvalues are in D. Okay? So I'm going to arrange the order of these eigenvectors such that for the associated eigenvalues, we'll call them lambda 1 through lambda n, they're going to decrease in magnitude. So the magnitude of lambda 1 is greater than or equal to the magnitude of lambda 2 all the way down to lambda n. So the nth eigenvalue is the smallest in magnitude. Whether it be positive or negative, it's just going to be the smallest in magnitude. Okay? So we're going to arrange the eigenvalues in that order, and then we're going to say, okay, these have the eigenvectors v1 through vn, and that's how we're going to arrange them. Okay. Now, because the eigenvectors v1 through vn, because they are linearly independent, what does that mean? It means that they form an eigenvector basis of Rn. I have n linearly independent vectors that span all of Rn. Okay, so these are going to form an eigenvector basis of Rn. They're just a basis of Rn formed of eigenvectors of A. These are an eigenvector basis of Rn. Now, when something is a basis of a space, it means that I can take any vector in that space and write it as a linear combination of those vectors. Okay, I can always write a vector as a linear combination of the basis vectors of that same space. So because v1 through vn forms a basis for Rn, okay, I can write any vector I want as a linear combination of them. So what I'm actually going to do, because we want to eventually end up with this linear system and dealing with that, what I'm going to do is I'm going to take my initial vector x0 in Rn. Okay, x0 is going to be an n by 1 vector. Okay, so if it's an n by 1 vector, it's got n entries in it, it's in Rn. So it's going to be a linear combination of those n vectors. So I can write x0 as c1v1 plus c2v2 up to cn_vn. Okay. Now, at the moment, x0 doesn't mean a lot to us, okay? All I'm saying right now is that it's an n-dimensional vector, okay? But what we are actually going to say is that this is going to be that initial state, okay? It's the initial vector. It's going to tell us the initial state of the thing that we are studying, whether that be the initial population of something or, I don't know, when we did the owl thing, as I said, it was the initial population in each of those age groups, okay? So it's always going to be the initial state vector. Now, multiplying by A will tell us what the next state is. So if I do that, to get x1, the next state, okay, in the spotted owl instance, that told us what the population was on the next month for each of the age groups of owls, okay? So x1 was the next state. It tells us what happens next in the population when you multiply it by A. So I'm going to go ahead and multiply x0 by A. Okay. Rearranging that, you're going to get C1 AV1 plus C2 AV2 up to CN AVN. Now, v1 through vn are eigenvectors associated with the eigenvalues lambda 1 through lambda n. So I know that AV1 is lambda v1, or lambda 1 v1, sorry, okay? Because it's got eigenvalue lambda 1 associated with v1, Same with AV2, that's going to be lambda 2 V2, okay? Because I know each one of those is an eigenvector. Multiplying it by A is the same thing as multiplying that scalar times the vector. So that's going to be C1 lambda 1 V1 plus C2 lambda 2 V2 up to Cn lambda n Vn, okay? You can carry on doing this, okay? If I found x2 would be A multiplied by x1. That would tell us the next state, what the next set of populations is going to be in the case of the owls, okay? So if I did A times x1, okay, I'd be multiplying this thing through by A, okay? C1, lambda 1, C2, lambda 2, etc. They're all just constants. So if I were to multiply that through by A, I'm going to get C1 lambda 1 AV1 plus C2 lambda 2 AV2. Okay, I can just pull those constants out the front of each term. No space there. Okay, so again, A times V1 is lambda 1 V1. So you could go ahead and do the same thing. So I'm going to get a lambda 1 squared here times V1 plus C2. Then I'm going to get another lambda 2 V2 here. So that's going to be C2 lambda 2 squared V2 up to Cn lambda n squared Vn. So you can keep doing this and multiplying by A. And all that's going to do is multiply it through by another one of these eigenvectors each time, eigenvalues, sorry, on each term each time, okay? So what you actually find is when you multiply A over and over and over again, to find the state of this system after k iterations, so by multiplying by A k times, what you find is that the kth state of it is going to be C1 lambda 1 to the k Vk plus C2 lambda 2 to the k Vk Cn lambda n to the k Vn. Sorry, I put a k on there by accident. That should be a 2. Okay. So that's what I get after k iterations. Okay. So multiplying by A k times in this system is exactly the same as taking each of my eigenvectors and pre-multiplying it by each of its eigenvalues k times, multiplied by those constants, where those constants were determined by that initial vector and what its linear combination was as a combination of the eigenvectors at the start. Okay, so C1 through Cn are going to remain constant depending on what your initial vector was. Okay, so each time you change what your initial vector is, that's going to determine what happens after k iterations, because that's going to determine what C1 through Cn are, and then whatever your matrix A is will determine what the lambda i's are and what those eigenvectors Vi are. Now, we're going to do an example. This comes out of the textbook. We're going to use a lot of the textbook examples in this, but I'm going to talk you through them a bit more than the textbook does, because some of these are very long and complicated, and I want to make sure that we're all on the same page, but they do actually do some great real world examples in the textbook, so I want to use those. This example, it goes off the back of when we were looking at the owl populations, but what it actually does, instead of just looking at the owls and their age groups, it looks at the owl population compared to the wood rat population, because owls eat wood rats. Okay, it forms the main part of their diet. So what they want to know is how the populations interact with one another. How are they related? Because of course, if you think about it, if owls eat wood rats, if the number of wood rats declines too much, then there's not going to be enough food for the owls, which means that they're going to decrease. If there's too many owls, they're going to be eating all the wood rats, which means that they're going to decrease suddenly. Okay, so depending on what happens with one or the other is going to affect the other population. Okay, so if there's a decline in one, it could cause a decline in the other, or if there's too many of one, it could cause a decline in the other, or too many of the other, etc. Okay, so what we're going to look at, okay, I'm going to say that xk is going to be the vector formed of the owl population after the kth iteration and the rat population after the kth iteration. Okay, so each of these vectors is going to give me the owl population and the rat population after k months. Okay, so this is after k months, and I'm going to say that each of OK and RK are going to be measured in thousands, because of course there's a lot of owls and a lot of rats, so trying to do this with thousands on it is going to be huge numbers. So I'm going to say that OK and RK are measured in thousands. Okay. What that means is each time I multiply by A, I'm going to be looking at what is happening the next month. Okay, because each iteration is going to be the next month's population. Okay, so I start out with my initial population at time 0, and then each time I multiply by A, I'm going to be looking at the population after 1 month. Okay, so someone else has worked this out, but they have said that this will make sense when you look at it. I mean, some of these numbers seem kind of weird, but in terms of whether they're positive or negative, it makes sense. And it's actually very similar to what we did when we did the spotted owl population. Okay. What this says, okay, take the top line, okay, this tells us what happens to the owl population at the next iteration, depending on what the current owl and rat population is. Okay, so you're at month K, okay, you have a certain owl population and a certain rat population. To determine what happens to the owls at the next month, so at month K plus 1, you're going to take this month's owl population and multiply it by 0.5, and this month's rat population and multiply it by 0.4. Okay, just looking at whether they're positive or negative right now. Okay, if you've got some owls that are there, okay, they're going to mate with one another. Okay, so you would assume that the owl population is going to increase. Okay, so that's why it's by 0.5, because you're going to have, I mean, some of them will die off, but they're going to mate with one another, and then you're going to end up with more owls than you started with. Okay, so that they're assuming that it's going to increase as you go along, and there's more being born than die. Okay, that's what they're showing you there. What they're showing you with the 0.4 RK is that you have to have the rat population increasing in order for the owl population to increase. Okay, so the owl population will increase as the rat population increases. Okay, because there's more food for the owls. If you look at this one down here, as the owl population increases, we have a negative here, and we're going to change the value of P depending on the situation. But as the owl population increases, this rat population at the next month will decrease, because the more owls there are, the more they're going to eat the rats, which means that the rat population will decrease. Over here, again, the more rats you have, they're going to mate with one another and give you more rats than you started with. Okay, now what this shows you here compared to owls and rats, okay, is rats probably have more babies than owls do. Okay, so these are going to increase at a greater rate than what the owls are. Okay, but what this shows you is because the owls eat the rats, as the owl population increases, the rat population the next month will decrease if there are too many owls. Okay, so let's put this into a system. Okay, we're going to specify P depending on what's happening. Okay, it just depends on like the environment that they're in, the number of owls at a particular like space in time, okay, that's going to affect what's happening between the rats and the owls, okay? So scientists go in and they determine what the value of P is for that particular time, and they say, okay, here is our matrix A. So what they're going to have is OK plus 1, RK plus 1 is equal to 0.5, 0.4, and then they're going to say that P is going to be 0.104 right now, and 1.1 times, okay. So this is of the form xk plus 1, so the population at the next month is this matrix A multiplied by the population at the previous month, so well, at the present month, okay? So you take what the population is at the present month, you multiply it by A, and that's going to tell you what happens at the next month. So when you do this, okay, and this is where all of these problems go, they're going to relate this system back to what we did here, this equation here. And that's going to tell us what the long-term behavior of this system is. So in order to do that, you need the eigenvalues and eigenvectors of A. Okay, you're going to need the eigenvalues and eigenvectors of A. So what that does, if this is A here, we're going to find its eigenvalues and eigenvectors, and I'll tell you what they are so you don't have to go ahead and calculate them. The eigenvalues, lambda 1 is equal to 1.02 and lambda 2 is 0.58. And then the basis of each of the eigenspaces is going to give us an eigenvector, which is V1 is 1013 and V2 is 51. Okay, so we found the eigenvalues and eigenvectors of A. Now, we know, because we've worked it out before, that we can write this kth iteration as C1 lambda 1 to the k V1. Now I've only got 2 eigenvalues and 2 eigenvectors here, so I've only got to go up to the second eigenvector. So that's going to be C1, then lambda 1 is 1.02 to the k times 1013 plus C2 times 0.58 to the k times 51, okay? So I know that I can write my kth iteration as this, okay? That kth iteration is the same thing as the kth iteration in here. So I could take this as xk minus 1 multiplied by A is going to give me the kth iteration, okay? And that kth iteration can also be written in this form. I want to know the long-term behavior of this. So as k goes towards infinity, what do these populations look like for a sufficiently large k? Okay, so as you've gone through enough months, what's going to eventually happen to these populations? Does it look like they're going to die out? Does it look like you're going to have an overload of one of these populations? What's going to happen? So let's look at what happens as k goes towards infinity. Okay. Now, if you look at this system and you plug in a sufficiently large k, what's going to happen? This thing here, 0.58 to the k, the larger the k is, the closer that thing's going to get to 0. Okay, if you don't believe me, plug it into a calculator with a sufficiently large k on it, okay? It's going to get really, really, really close to 0. So this whole term, as k goes to infinity, this whole term is going to tend to 0. What happens to this term? Well, as k goes to infinity, this thing's going to shoot off, okay, and get larger and larger and larger because it's greater than 1. It's got a magnitude greater than 1. So this thing's it's not going to go off to infinity very quickly, but it will shoot off to a sufficiently large number, okay? So what that means is this whole term here is going to dominate the system, and this term will tend to 0. So for a sufficiently large k, So as enough months have gone by. So we're going to assume that C1 is greater than 0. That's just a generalization. If it's negative, the problem that you actually have is that this thing's going to go off to negative infinity. You can't really have a population go to negative infinity. It doesn't make sense because it either goes to 0 or it shoots off to some large number. So you can't have a negative population. So we're going to assume that C1 is greater than 0. And what that's going to do for a sufficiently large k, that xk is going to approximately equal C1 1.02 to the k 10 to the 13, because this other term here is going to go towards 0. It's going to be very small, very insignificant in the grand scheme of things. So for a sufficiently large k, this is what we have. Going back to our actual system, we know that xk plus 1 is a times xk. Okay. We also know that xk plus 1 would be this thing, but with k plus 1 plugged in. So this xk is going to roughly equal C1 1.02 to the k plus 1, 10, 13. Okay. I can rewrite that. I'll actually do this again on a new page. So xk plus 1 is approximately equal to, we said it was C1 1.02 to the k plus 1, 10, 13. Okay, so I can rewrite that as 1.02 times C1 1.02 to the k, 10, 13. So all I've done is I've pulled out a 1.02 from that term and brought it out the front. This thing here is xk. So that tells us that xk plus 1 is approximately equal to 1.02 times xk. So going back to what our x's actually are, this tells me that every month as k gets sufficiently large, I would assume that each month for a sufficiently large k, that my population of both my owls and the rats increases by 2% on average. Okay, so what this tells me is eventually after enough months, both the owl and the rat populations increase by roughly 2% every month. Okay, so once we're far enough away from our initial value, okay, from our initial population, and after enough months have passed, we would assume that on average the population of each one would increase by 2%. So let's look at how we did this again, just to recap, okay, because we're going to be coming back to these systems. What we said was that this system, okay, can be written as one of those difference equations. It can be written as a dynamical system, where it's an iterative system. So to find the population of the next month, I just multiply the population of the current month by this matrix A. And that is determined by the system that you are given, where they relate the owl and the rat populations to each other. Okay, some will increase, some will decrease, depending on which one increases or decreases, okay, because owls eat rats and that's going to affect the population. So they'll give you this relationship between the populations. You can then write that as an iterative system, okay, which is of the form xk plus 1 is equal to a times xk. Because this can be written as an iterative system like that, we can come back to here and say, well, I know that that A has eigenvalues lambda 1 and lambda 2, and it's got eigenvectors v1 and v2. So what I'm going to do is I'm going to write the kth iteration in terms of its eigenvalues and eigenvectors, as we see at the bottom here. So I'm going to go ahead, because I know it can be written as this, I'm going to go ahead and write xk, the kth iteration, in that form, in terms of the eigenvalues and eigenvectors, which is what we did. Then you can see that because one of these eigenvalues has magnitude less than 1, that thing will go to 0 as k goes to infinity. The other one has magnitude greater than 1, which means that that will be the dominant term, because that one will get larger and larger and larger as k goes towards infinity. So I know that the kth iteration for a sufficiently large k is going to tend towards this value, which means that then when I look at my k plus 1 iteration, okay, I can plug in xk plus 1, so I'd plug in k plus 1 to here, and that's going to give me this, which then means I can plug in, or I can separate actually, 1.02 and then xk. So I get my xk term times a constant. And that tells me that on average, for a large enough k, my populations are both going to increase by 2% every month after enough months have passed. Okay. So what we can see here is, in this case, you have a dynamical system where you got that matrix A. That matrix A had 2 eigenvalues, one of which had magnitude less than 1, one of which had magnitude greater than 1. But because that one eigenvalue had magnitude greater than 1, and the other one, when we put it into the system, that term would tend towards 0, we know that our system, our kth iteration, will tend towards the term with the eigenvalue that is got magnitude greater than 1. We know that xk will tend towards this. Okay, that happens with any system. So if you have an A that is greater than a 2 by 2, it could be a 3 by 3, 4 by 4, etc. As long as it's diagonalizable and you can write it in this form in terms of its eigenvalues and eigenvectors, when you do that, if you end up with a system where you have an eigenvalue that has magnitude greater than 1, but all other eigenvalues have magnitude less than 1, that means that all of these other terms that you see, like this one here, all the other terms where the eigenvalues have magnitude less than 1, all those terms will go to 0 as k goes to infinity, which means that it is always that dominant term that has the eigenvalue of magnitude greater than 1 that's going to dominate the system, and that's what that kth iteration is going to tend to as k goes towards infinity. So if you ever have a system where it's got one eigenvalue with a magnitude greater than 1 and all other eigenvalues have magnitude less than 1, then it's going to tend towards that one dominant term. Okay. We've looked at a 2 by 2 system here. Okay, A is 2 by 2 matrix. We're going to carry on with 2 by 2 matrices in the next video. And we're going to look at what happens when you have 2 eigenvalues that have magnitude greater than 1, 2 eigenvalues where they got magnitude less than 1, and if you've got one that's greater than 1 and one's less than 1, what happens there? Okay, we're going to look at these different situations. We're also going to go into complex eigenvalues, and we're also going to look at systems first that have got eigenvectors that are just the standard basis 1, 0 and 0, 1, and then we're going to extend that and generalize it to other eigenvectors. And we're going to actually draw these things out and draw the trajectories, that's a difficult thing to say, draw that out so that we can actually see what happens in these systems. Okay, so you can actually see it geometrically as to where these things are going to shoot off to. Okay, so we're going to do that in the next video. As I said, 5.6 is a long chapter. So go ahead, if you need to rewatch this or look at it again, by all means do that. If you want some practice problems for this, I will be assigning some on the homework for this Friday, so you can have a chance of working through some of these problems and seeing what these actually look like and what they're going to tend to for some of these real world problems. Okay. If you have any questions, let me know, and I will see you in the next video for the second part of 5.6.